What's going on, everyone? Welcome back to another episode of Crypto Catch Up with me, Benny. In this video, we're going to be going through some more educational content around interplanetary file systems, better known as IPFS. Now, IPFS has been around for a number of years, and it's not specifically something that's related to blockchain technology, but it's something that a lot of blockchain projects are starting to utilize in their architectural stack. And the reason for that is if you want to store any data, a lot of these platforms are talking about being decentralized, being immutable, and IPFS allows for exactly that. So we're going to go through all those details. So let's get into it. Alright, well, IPFS was originally created by a gentleman by the name of Juan Benet back in 2014. Now, originally it was a project for himself. He has a company called Protocol Labs. Now he's made that project open source so the rest of the world can benefit from it. Now, it is something that is actually, really forward thinking and quite, incredible what he's actually achieved here. It's currently written in Golang, JavaScript, and also a Python implementation. Now, where Juan, I guess, was going with the whole thinking around this particular interplanetary file system was exactly that. If we were to colonize another planet, Mars, Jupiter, Venus, whatever it may be, how would our internet work? And that's something that he thought about, because currently with our internet and the way that it works is by utilizing a protocol called HTTP. Now, HTTP is Hypertext Transport Protocol, and like we've just said, it's a protocol for data communication, essentially sending data back and forth on the World Wide Web or the internet. Now, it was brought out originally in 91, and better recognized, I guess, than in 1996 when it started to be used in web browsers. Now, the downside with HTTP is that it's actually quite a inefficient protocol. Now, we don't personally notice these inefficiencies so much because there's servers, possibly quite close to us that are taking and caching a copy of it. So, for example, if I'm wanting to download a picture of a cat, I search for cats on Google, and if somewhere in Australia is a server farm in Sydney, for example, has already downloaded that, it will retrieve me that content from there rather than having to possibly go all over the world. And that's done by Google's servers, and they're all around the world to be able to make that content delivery, a lot faster for us. But there is downsides to that. Now, HTTP has been the backbone of the internet for 20 odd years. So it's something where, it's time for a change. And this is where the whole Web 3 is coming into play. Now, HTTP is expensive in terms of bandwidth because of the way it works. And we're going to talk about that in a moment's time. There's also the issue with file duplication. So if I upload a photo of cats and you upload the exact same photo of cats, it doesn't just have that one copy of it. It just keeps allowing people to upload these same freaking copies of cats, which is obviously inefficient once again. It is centralized. So, these large server farms that are run by Google and Facebook, you are, going to them to get your content every time. And because of that, they're censorable. So if a government came along and goes, whoa, what Google is doing is wrong, I'm not going to allow for this anymore in their country, they could shut down those data centers in those particular countries, and then we wouldn't be able to query for that particular information. Then you end up with things like this, the file or the directory is not found, or maybe even the internal server error. Very sad times. Now, what is all of this? Well, HTTP uses something called location-based addressing. And so what we know that as, so if you could imagine you're on the left-hand side with your mobile phone or your computer, and you type in, let's go to google.com. Google.com essentially is for us a very nice way to know a location. The location is Google that we're trying to find, or if we're trying to search cats, it could be Google Cats that we're actually searching for. But in the background, there's some other technology there called DNS, or domain name servers, that is translating the IP address, which is the numbers that I've put on the screen there, which is actually Google's DNS server for us. So we search for it, it then goes and finds it at a particular location, that 8888, which is a server somewhere specifically, and it retrieves that content back to us. Now, the downside for that is, and an example of, is that if we were sitting together in a room right now and I upload this video and I go, hey, you know, how cool is this? And you go, oh yeah, that's a cool video, I should like and subscribe. If you were to want to look at that content on your own phone, you wouldn't just be able to, you know, download a cached copy from me, even though it's on my computer and readily available. You would have to, you know, go all the way up to Google, to YouTube, and then YouTube, you'd have to download it from there to watch the video. That seems obviously, you know, quite inefficient, considering I have a copy right here I could possibly share with you. So, what then is IPFS? Well, IPFS is a peer-to-peer distributed hypermedia protocol. So essentially, it's HTTP, but IPFS. Now, what IPFS essentially does is think, you know, more broadly in terms of how can we, you know, have an addressing system that doesn't look for a particular location that may be moved or changed, like a book in a library. How can we do it based on the content? And how can we do it in such a way that makes it immutable, that we know when we're downloading a file that it's the file that we're looking for? Well, they do this in a way, obviously within that peer-to-peer network, that has no single point of failure because it's distributed. And this is where it shares a lot of common properties with obviously blockchain related technology. Now, IPFS uses something called content-based addressing, which is very different to that of location-based addressing. So with content-based addressing, and we've got a little image here, is that, you know, you can see HTTP there, everyone's looking for something, but everything they're looking for is that central location on a single server somewhere in the world. Whereas with content-based addressing, what IPFS does is use cryptographic hashes, which we've done a video on in the past, and it allows you to practically look for that particular hash. So the input data, and what we've talked about it being deterministic, that if it's the same input data, you'll get that same output hash if you use the same algorithm. It removes duplication of files. It also means that we can search based on a hash or based on something else. So if I search for cats again, it would find cat hashes and allow me to, you know, go off and get a copy of that file from essentially anybody that is storing a copy of that, rather than just the local server, which could be thousands of kilometers away. Now, with that, let's see what's next. With IPFS, it's actually stored as objects. Now, each object are 256 kilobytes in size, or a maximum size of 256 kilobytes. They link to others, whereby if it's larger than that, they can practically break it down into smaller objects and link them all together. They're immutable because they use cryptographic hashes to secure an object to say, yes, this input data is, you know, equivalent to this particular output hash. And there is versioning as well. So it is not just, you know, one copy. You know, if you need to upload a file like we do, sometimes we upload, you know, Word documents and we need to make a new version of that. You can. And it allows for any file size. And what I've done is just done a really quick diagram for you all around the versioning. And what it does is in these objects, if you could imagine these are IPFS objects, the P and the O, if you can see it there, P stands for parent, O is for object. And if we had version 1 of a document and then we changed it to version 2, essentially the parent gets linked back to the original parent. And then that's how it versions it. So it's just like Git, if you are aware of code repositories. The second one I want to show you here is in terms of large files. So as we've said on the screen there, 256 kilobytes is all that it allows for. Well, how do you do it? Well, if we were to take a 1 megabyte file of this beautiful dog or cat or whatever the hell I've drawn here, it would break it up into 4 objects of 256 kilobytes each. And what it then ends up creating is an empty IPFS file, which practically links these. So this is data, and that's L for link, and they links all of those objects together. So if you search for something on one, it then can go essentially and put this file back together for you, which is quite amazing stuff. Now, this is just a high-level overview of what it does. So like we've just talked about, each file, picture, text file, whatever you want, gets its own cryptographic hash. And what that means is essentially, we know if we're downloading that file, if that input is actually the correct file. The second thing is it removes duplications, because if we have a cryptographic hash, we know that obviously if the same input gets the same output, that if there's any duplication of that, it just simply won't save it because it already knows it's got that somewhere else. Each network node only stores content that it's interested in, and we'll talk about that shortly in terms of projects. And when you're looking up the files, you're asking the network to find the node storing the content behind the hash instead of a particular location, because if that location goes away, what are you going to do? Whereas if you have a particular hash and multiple copies, like a distributed ledger of a blockchain, is being used, then you have the ability to obviously get that file. And what I want to do just quickly here is to show you what I mean around that cryptographic hashing when you have the same input with a file, what it would mean in an IPFS. So we're going to do a live demo of running IPFS on my computer here, just to show you that and how you can access it from online as well. So if we get out of that, what I'm going to do is show you here, I've got a file. So I'm just going to save this location. So we've got some bananas. We've got two pictures of Dorian, which was mistakenly confused as Satoshi Nakamoto. And you'll notice that I've labeled them differently, Satoshi_1 and Satoshi_2, but they're exactly the same file. So what we've been talking about is they should render the same output hash, and it shouldn't actually store both of the files in the folder. It should only store one. And I've just got a text file here that says hello everyone. So if we go to our command prompt here, IPFS is running on my computer. So what we do first, just to make sure it's working, we go IPFS help and we get a return. So what we'll do is just put this over here and put this up here. So you can see here that it says global peer-to-peer Merkle DAG file system, because IPFS does use a Merkle DAG. So if you are wanting to know about cryptographic hashes or Merkles, I've done 2 videos on that in my educational content. So the next thing we're going to do, I can't see my keyboard really well here from my microphone, so IPFS init, which is to initialize it, and what it's done here is generated a key pair, and I'm just going to copy this in here just to show you that we have got IPFS up and running, ready to rock and roll. The next thing we want to do is add the files from that test directory. So IPFS, add R for repository there, and then I'll just paste, not that one, because I copied the other one. Let me go back and get this. Let's get this one back. I need the right one. Boom. All right. So what you can see here is that we've got bananas, hello, Satoshi 1, Satoshi 2, and the test here. Now what you'll notice though is that Satoshi, both of these here, though it's got a different name, the actual algorithm, the cryptographic hash, has worked out that the input data of both those images is exactly the same and has given it the exact same output. So it's not storing both of those files. What we're now going to do is go and run it as a local host, so we can show, from a network perspective, how you could access these files from content-based addressing rather than location-based addressing. So next thing we do here is IPFS. We need to run the daemon, which is essentially a background process. It's going to install the daemon. Now, just so you know, guys, I am using a dongle to run my internet connection here to make sure that no one in the world is going to be hacking my connection, because I only use this very rarely. So thanks for coming. So it says it's ready. So what I can do now is take one of these cryptographic hashes, and this is the content address, everyone. So we're going to go up to here and I've put in the local host already, ready to rock and roll, and I just put that hash in. Bam, there it is. Of course, if we want to have a look at some bananas, we can do exactly the same thing. Beautiful bananas. Cavendish, ladyfinger, whatever you like. And finally, we'll just check out our text file here, make sure we can say hello to everyone again. Make sure that works. And there it is. Hello, everyone. So what I've just shown you here, guys, is content-based addressing. It's based on this cryptographic hash, which means it only needs to store one of any particular file at any particular time, which is absolutely awesome. So where can we utilize it? Well, archivists, service providers, researchers, developing world, blockchains, content creators, all of them can utilize this particular project. Projects next. Now with projects using IPFS, you got Filecoin, which is from the creators of IPFS, Storage, Sia, Swarm, DTube, which is essentially a decentralized YouTube. They're all utilizing the IPFS protocol as decentralized storages. So if you can imagine Google, Cloud or Google Drive, it's exactly like that, but obviously using a cryptocurrency based one like Storage or Sia Coin. Now, if we go back to the whole purpose of, why IPFS came along, well, it's because of the inefficiencies we talked about, but it's also because of the way that you can do content-based addressing, and that's really the crux of what's going on here. So if we were on the moon, and it does take for us, for example, to send a piece of data from, let's say here in the world to the moon and back, on a good day, it might take 4 minutes for it to transfer. On a bad day, it might take 48 minutes to transfer. So for a round trip, you're looking for an hour just to get a cat, picture back. It's far too long. And this is essentially what this project or what this protocol addresses, is that by using content-based addressing, if somebody on the moon already had downloaded that image, it would cache that and they would have a copy of it for you to download directly from there, rather than having to come back to Australia to get it from the server for it to be, provided back to you. Alright guys, that is IPFS. I hope you like the demo involved. Every time I try and do an educational video, I'll try and get a real life demo for you. But please, if you have any questions, put them in the comments below and I'll answer them for you. Once again, everyone, thank you for watching. Please like and subscribe and we'll get another educational video out for you soon.